In this module, we will talk about the Langmuir model of adsorption and the Langmuir isotherm. In the study of adsorption processes, the Langmuir model stands out as the simplest yet physically plausible kinetic model. While discussing the Langmuir model of adsorption, we come across the concept of an adsorption site. Adsorption site refers to a specific location on a solid surface where a molecule from a gas or liquid phase can adsorb. The nature of these sites depends on the surface properties, including its chemical composition, structure, and electronic characteristics. The Langmuir model of adsorption is based on the following assumptions. The model assumes that all adsorption sites on the surface are equivalent in terms of their ability to adsorb molecules. The surface is homogeneous without any variations in adsorption properties across different areas. Adsorption can only occur at unoccupied sites. Each site can hold only one adsorbate molecule at a time. The presence of a molecule at a site prevents the adsorption of another until the first is released. Adsorption and desorption are uncooperative processes. It means that the probability of a molecule being adsorbed at a particular site is considered independent of whether neighboring sites are occupied or not. This assumption implies that there are no interactions between adsorbed molecules. Finally, the adsorption process is restricted to the formation of just a single layer of molecules on the surface, a monolayer. This means that once all adsorption sites on the surface are occupied, there is a monolayer of the adsorbate covering the surface and no additional adsorption can occur on this surface. In the Langmuir model, the adsorption process is understood through a dynamic adsorption equilibrium between the molecules in the gas phase and those adsorbed on the surface. This equilibrium is represented by the following mechanism. Here, Ag represents a molecule in the gas phase, while M surface denotes an unoccupied adsorption site on the catalyst surface. When a molecule A adsorbs into the surface, it occupies a site, forming AM, which is the occupied adsorption site. The rate at which molecules adsorb onto the surface is governed by the adsorption rate constant Ka. Conversely, the rate at which molecules desorb from the surface back into the gas phase is controlled by the desorption rate constant Kd. The balance between two processes, adsorption and desorption, determines the fractional coverage of the surface at any given time. The coverage is a function of the partial pressure P of the adsorbing gas A. The rate of adsorption is influenced by two factors: the rate of molecular collisions with the surface, which is proportional to the partial pressure P of the adsorbate, and the availability of unoccupied adsorption sites. If the total number of sites is n and the fractional coverage is theta, then the number of unoccupied sites is n times 1 minus theta. Consequently, the rate of adsorption Va can be expressed as Ka times P times n times 1 minus theta. Conversely, the rate of desorption is proportional to the number of adsorbed molecules, which is equal to the number of occupied sites, n times theta. The rate of desorption d is then equal to kd times n times theta. In equilibrium, the rate of adsorption equals the rate of desorption, leading to no net change in surface coverage. This condition is formulated by this equation. This equilibrium condition can be further simplified to express the relationship between fractional coverage theta, pressure P, and the equilibrium constant of adsorption K adds. Theta divided by P times 1 minus theta equals the K adds. Adsorption equilibrium derived in the context of the Langmuir model can be compared to an equilibrium in a chemical reaction. In this analogy, the adsorbed molecule Am is considered the product, while the free molecule A in the gas phase and the free adsorption site M on the surface are analogues of the reactants. The adsorption and desorption processes are analogous to the forward and reverse reactions, respectively. The equilibrium condition in adsorption is similar to that in a chemical reaction, where the rate of the forward reaction, adsorption, equals the rate of the reverse reaction, desorption. This balance is described by the equilibrium constant K adds, which in the case of adsorption is given by the ratio of the rate constants for adsorption and desorption. The equation for adsorption equilibrium is completely analogous to the equation for the equilibrium constant in a chemical reaction, where the concentration of products over the concentration of reactants is considered. In the case of adsorption, theta is an analog of the concentration of the product adsorbed molecule Am, while P characterizes the concentration of the first reactant, the free molecule A in the gas phase, and 1 minus theta is an analog of the concentration of the second reactant, free adsorption sites M on the surface. Similar to the equilibrium constant in a chemical reaction quantifying the tendency towards the formation of products, the equilibrium constant of adsorption K adds quantifies the tendency of a molecule to adsorb onto a surface. A higher value of K adds indicates a stronger affinity of the adsorbate for the surface. The rearranged form of the equilibrium equation gives us the Langmuir isotherm. Note that the equilibrium constant has the dimension of inverse pressure. This figure illustrates Langmuir isotherms. It shows the variation of the surface coverage determined according to the Langmuir model of adsorption with pressure for different values of the equilibrium constant. As the equilibrium constant decreases, higher pressures are required to achieve complete surface coverage. This trend reflects the weaker affinity of the adsorbate for the surface as quantified by the equilibrium constant. The Langmuir isotherm is an important equation in the study of adsorption. The relationship between the surface coverage and the pressure of the adsorbing gas is critical in various applications, such as catalysis, where surface interactions play a key role. In the context of Langmuir isotherm and adsorption in general, temperature plays a significant role in determining the adsorption behavior. The equilibrium constant of adsorption is inherently temperature dependent. Recalling an analogy with the chemical equilibrium, the temperature dependence of the equilibrium constant of Adsorption is given by the enthalpy of adsorption. As it can change with coverage, strictly speaking, we should talk about the isosteric enthalpy of adsorption, which is the standard enthalpy change for the adsorption process at a fixed surface coverage. This value is typically negative, indicating that the adsorption process is exothermic. The exothermic nature of the adsorption leads to higher adsorption at lower temperatures. This behavior can be understood as being due to the increased kinetic energy of the gas molecules at higher temperatures, which makes them less likely to be adsorbed and more likely to desorb if already adsorbed.